This is the lecturette for sections 14.1 and 14.2, where we introduce chemical kinetics and reaction rates. Chemical kinetics is the study of rates of reactions and what we can tell about how molecules are acting from those rate studies. So in these particular first two sections, we're going to look first at control of reactivity, and we'll look at the two major areas of control, thermodynamic control and kinetic control. And for kinetic control, we'll describe collision theory, which we'll come back to at the end of this chapter as well in more detail. And then we're going to look at ways that we describe reaction rates. That is, we'll be talking about reaction rates, and so the first thing we need to do is talk about in fair detail what we mean by that. So first what we're going to do is we want to talk about, step back a little bit and talk about what controls whether reactions happen or not. And there are two broad controlling factors for whether something chemically occurs or does not occur. First is thermodynamics. And thermodynamics asks the question, are the products more stable, that is, are they lower in energy than the reactants? The second thing is kinetics, and that is, even if the products are more stable than the reactants, and the reactants would be energetically favored to turn into the products, does that actually happen at a significant rate? And the term significant rate is dependent on one's opinion and one's needs. If you are burning wood in a fireplace, that could be, burning over a period of, an hour or half an hour, or 2 hours or 3 hours. If you're exploding gasoline in a car cylinder, the significant rate needs to be much, much faster than that. It has to happen much, much more quickly. And if you're a geologist, the significant rate might be millions of years. But depending on whatever rate domain you choose, for a reaction to occur on the time scale you need or you're interested in, it must be favored both by thermodynamics and kinetics. So let's look at this in a little more detail. For thermodynamic control, there's two parts to that. And that is, there's enthalpy, which has to do with bond strength. And stronger bonds equal lower enthalpy, which means a lower energy, more stable compound or system. So strong bonds favor reactions occurring. So formation of strong bonds during a chemical process favors that process occurring. Entropy has to do with free motion of atoms. And the freer the mobility of atoms and molecules in the products means a higher entropy, and that actually makes for a more stable system, a more likely to occur system. And so for systems that have more independent particles, for example making a gas, we'll see later on, those favor reactions as well. For many chemical systems, enthalpy and entropy kind of counteract each other. That is, the system that the reaction under study will be favored by one of those and disfavored by the other. And when that happens, temperature is going to play a role, and favorability depends on whether temperature is high or low. And in some cases, it's favored high temperature. Some cases, it's favored at low temperatures. Kinetic control has to do with three things as well. It has to do with activation energy, which is the energy barrier reactants must overcome to react. That is, even if the reaction gives off energy overall, there's always some barrier you need to get over to get the reaction to start. And that's called the activation energy. The concentration of the reactants, and that has to do normally, but not always, that the greater the concentration, the greater chance there is for the reactants to encounter each other, and when they encounter each other, they can react. So generally, greater concentration leads to a more likelihood that reactions will occur, and they'll go faster. But that can sometimes be not true. And finally, temperature. Higher temperature increases the number of collisions that happen between reacting molecules, and it also increases the fraction of those collisions that overcome the activation energy. So in general, higher temperature leads to faster reactions. So those three things together play roles in whether or not reactions are kinetically controlled. And so graphically, enthalpy, entropy, and temperature combine to give thermodynamic control. Activation energy, concentration, and temperature combine to give kinetic control, and both of these must be favored for the overall reaction to occur. Okay, now let's talk about this kinetic control on the molecular scale, and we do this using collision theory. And the idea is that for a reaction to take place, what must happen is the molecules, let's say you have two different molecules, let's say we have NO reacting with ozone, O3. The molecules have to collide. They must do so in a correct orientation, and they must collide with enough energy to overcome the activation energy. So in this case, what's going to happen is an O3 molecule is going to hit an NO molecule, and this oxygen right here is going to go from the O3 and end up attached to the NO, which is why we end up with NO2 and only O2. For that to occur, the oxygen and the nitrogen need to form a bond, and therefore they must collide with the oxygen hitting up against that nitrogen so they can form that bond. So that's the correct orientation there. So that's okay. The other thing that has to happen, though, is you have to break this bond here. That bond has to break. And that bond breaking process is related to the activation energy. And so in order for the reaction to occur, you have to have this collision occur with enough energy that that bond can be broken. Even if you get more energy out later on when you form the bond between the oxygen and the nitrogen, you have to have enough energy to overcome that initial bond break process. So let's take a look at a better, more visual example of this orientation effect. In this reaction, we're having a chloride ion, which has 4 lone electron pairs, reacting with a carbocation. A carbon compound has a cation. So this carbon atom is short 2 electrons, so this is just going to form a bond there. So you're going to form a bond between the chlorine and the carbon. For that reaction to happen, the chloride ion, must attack, is the way we say it, that central carbon atom. So if it actually hits here, it can form that bond and the reaction can take place. So that's a good orientation of a collision. If instead the chloride ion hits at the top of the molecule up here, it can't form that bond because it's not hitting the right place. So that's an ineffective collision. And so the reaction will depend on what fraction of the collisions, the molecules bouncing into each other, do so where the chloride is close enough to that carbon to form that bond. So mathematically, the rate is equal to this equation, this general equation, where there's a pre-exponential factor, which is related to the fraction of collisions with the correct orientation, times this exponential factor, which is the fraction of collisions exceeding the activation energy. And then this factor is concentration control. And so most reactions depend in some way on the concentrations of the reactants. And we'll talk about how, in great detail, how we find that out later on. Okay, now we're going to turn to expressing the rate of the reaction. There's a number of ways to do this. The first thing is we often do it just graphically, where what we do is we make a graph of concentration of either a reactant or a product over time. And so the start of the reaction is here at time equals 0, and the reaction goes as you go from left to right. And so as the reaction goes, what happens is a reactant will decrease, and a product will normally start at 0 and increase. And so in this particular case here, what we have is we have A decreasing, and we have B increasing. And in general, the steeper the slope, either positive or negative, the steeper the slope, the faster the reaction goes. So the reaction is fast here and here where the slope is steep, but when you get down over here, the reaction is quite slow, and eventually it pretty much stops. So a low slope, a small slope, is a slow reaction. A steep slope is a fast reaction. And so what you can see in this particular case is what's nice about this graphical thing is you can see that the reaction slows down as it occurs. So the reaction starts fast and it gets slower. The other thing you can see here is that the rate of the formation of B is twice the rate of the diminution of A. And that's because you are actually making 2 of these molecule B's for each molecule A that gets used. So the rate of B formation has to be twice the rate of A consumption. Now we're going to look at doing this mathematically. So mathematically what we do is we have a number of different ways we express rate. And the first thing we're going to talk about is average rate, where what you do basically is you take this plot of concentration versus time, and let's say of a reactant, and you basically take 2 points here and here, and you take delta concentration and delta time, And the rate is equal to delta concentration over delta time. That is, how much is the concentration changing per minute or per hour or whatever. And so if we look at it, the concentration of B starts, if we want to do like the rate in the first minute, starts at 0 and ends up being 0.5. So the rate of appearance of B is the change in concentration times the change in time. So it's the final concentration of B final, that's at after our minute, that's 0.5, minus concentration of B initial, which was 0 to start with. So that's 0.5 minus 0, divided by the time, that time final over time minus time initial, so it's divided by 1 second. So it's 0.5 molar per second. It means the concentration changes by 0.5 moles per liter per second. The rate of appearance of A is, or disappearance of A, is minus the change of A divided by the change in time. And it's an important thing to know that rates are generally written as positive numbers, and then you describe whether the constant is changing positively or negatively in terms of whether it's a reactant or a product. And since A is a reactant, it decreases. So it starts at 0.5, it ends up at 0.25. So the rate of change of A is 0.25 minus 0.5. So that comes out to minus 0.25 divided by 1, but there's a negative sign there because we're talking about it going away. So the rate's 0.25 molar per second. Notice that the rate of change of B is twice the rate of change of A, and that's because there are 2 B's for each A, so that makes sense. In general, stoichiometry relates to rate of reactions by each rate is relative to its stoichiometric coefficient. So if you have A numbers of A molecules reacting with B numbers of B molecules to make C numbers of C molecules and D numbers of D molecules, the rates of those will be linked in this manner. Notice that the negative signs are present for the reactants because they're decreasing and are absent for the products because they're increasing. So let's take a look at a further example of that. Here's an experiment where we watch hydrogen peroxide decompose. And if you did this graphically, what you would do is you would put minutes here, and you'd have points at 4:34, at 8:68, and at 13:02 minutes. And we'd have our concentration here, and the highest concentration is around 0.1. So if that's 0.1 there, we start around 0.09, then we're around 0.56, then we're around 0.35, then we're around 2.8. So basically we have this curve. And what we're doing is we're going to find the rate of disappearance of H2O2 in the first 434 minutes. So we're going to go from there to there. So the rate is going to be change in concentration of H2O2 divided by, or minus that because it's decreasing, and divided by the change in time. And so our concentrations change from, our final concentration is going to be minus our final concentration, which is 0.0566 molar, minus our initial concentration, which is 0.0912 molar, over the change in time, which is 434 seconds, or minutes, sorry, minus 0 minutes. Now, so when you divide that out, you come out with 7.97 times 10 to the minus 5 molar per minute. If we do the same thing for the rate of appearance of O2, notice we don't have anything for the appearance of O2 here, but we know that for every 2 of these that react, we have to make 1 of these. So the rate of appearance of O2 must be half as large as the rate of disappearance of that. So the rate of O2 appearance is going to be 7.97 times 10 to the minus 5 molar per minute divided by 2. Which is 3.99 times 10 to the minus 7th molar per minute is the rate of appearance of O2. We have 2 other ways that we, related ways that we express rate. One is called an instantaneous rate. This is the general kind of thing. And that is how fast is the reaction rate at any particular instant. And the answer for that is that it's the slope of the concentration time curve. So if you, at any place along the concentration time curve, draw a tangent line, the slope of that tangent line is the rate at that time. And finally, one of the most important rates that we use is called the initial rate. It's the rate right at the beginning of the reaction. And it's just the instantaneous rate at time zero. So if you draw the tangent to the line right at the very beginning and take the slope of that tangent, that's the instantaneous rate at time zero. That's the initial rate. The reason the initial rate is really important is that that's the one place, the one time during the reaction where you are sure of what the concentrations are, because you mix your concentrations and add them together, so you know the concentrations at that instant right at the beginning. And so it's easy to examine reactions by looking at the concentrations right at the start.